Hi everyone, thank you so much for joining us. Welcome to another episode and actually session of the AFMC seminar series. And today, actually, Dr. Zhongzheng Wang will deliver a talk about the subtle power of the capillarity, what wet grain, moving droplet, and the porous media flow have in common. So, actually, Dr. Zhongzheng Wang is a lecturer in the School of the Mechanical, Medical, and Process Engineer at the University of the QUT. So thank you so much for accepting our invitation, Dr. Zhongzheng, and the floor is yours.
Thank you very much for the introduction. It's an honor for me to present in the community. So I'll just get started. Today, I'll talk about some interesting research I have been doing in the past few years on the topics of capillarity. So first of all, just a quick introduction about the interfacial tension. Because the system tends to move towards the minimum energy, liquids tend to adjust its shape so that the surface area is minimized. Surface tension is a measure of energy required to increase the surface area by 1 unit area. So the unit of that is energy per area, so joule per meter square. And then if we consider this liquid film over here with a rod that can be moved, then we can just assuming it moves by 1 unit length dx. So the change of energy or the work required is equal to the surface energy per unit area multiplied by the area. So that's based on the original definition, we got the surface tension multiplied by 2 times L, the height, times the width of the moved distance. That's just the area. And then we have 2 over here because we have two surfaces. One is the surface we see, and the other surface on the other side of the screen, which taking into account the total area. And this is also equal to the force multiplied by the distance. So if we rearrange this equation, we can also see that the surface tension can also have a unit of force per unit length. Both of this kind of definition can be useful when deriving the governing equations, either through the unit, through the energy per unit area or the force per unit length. And another important factor when talking about the surface tension is wettability, the contact angle. That is relevant when the liquid comes into contact with a solid. So here we have two photos showing that water sitting on an aluminum or a plastic foam cup. You can see clearly the wetting behavior of these two liquids are quite different. One is hydrophilic, one is hydrophobic. And correspondingly, there are a few famous equations involving contact angles. For example, the contact angle of the fluid on a surface can be calculated by the Young's equation depending on the interfacial tension of solid gas, solid liquid, and liquid gas. And then we have the Jordan's law describing if we have a capillary tube, then how much the liquid will rise up by balancing the gravity and interfacial tension. Then we have the Washburn's equation. Basically, if we have a liquid moving in a tube horizontally without consideration of gravity, then the motion of fluid can be described by taking into account the surface tension force and the dissipating viscous force. And then we have, in the end, the scaling of the distance is equal to square root of time, as well as other parameters like the size of the tube, the contact angle, and the viscosity. So there are quite many interesting applications of capillarity. First of all, it is possible to utilize the surface tension to spontaneously move this droplet. You can see that once the droplet is deposited on a surface, then it moves upwards in the opposite direction of gravity. And this spontaneous movement can be utilized in applications, for example, fog harvesting, where the a liquid condenses on a surface and then coalesces into droplet and rolls off. And then it's also possible to spontaneously separate mixtures of immiscible fluids, such as water-oil mixtures. We have a mixture, and then spontaneously the liquid will move, the water will move towards the left, and the oil will move towards the right, because there's a preference in terms of the wetting of the solid. The other field where the surface tension is important is in granular materials. So if we have spherical, let's say, grains, adding a bit of water will lead to potential liquid bridges. You can see that a small amount of water can form between those two particles. And these liquid bridges may change the overall behavior of the granular materials. So maybe initially they are cohesionless, but adding a bit of water, there's a interparticle attractions between particles, making the granular materials cohesive. And then that could lead to interesting phenomenon. For example, the collapse, the drying induced collapse. So initially it's cohesive because of the existence of liquid bridges, but after drying, they collapse. Lastly, I want to mention the application of multi-phase flow in porous media. So in the engineering application of carbon geosequestration or enhanced oil recovery. So basically one fluid is being pushed into the porous media to displace the other one. And then the capillarity or the surface tension during this system will have a significant role in terms of how much, for example, CO2 you can inject within the reservoir and how stably they can be trapped for long term. In today's talk, I'll give a bit of introduction, which I think already done, and then we'll focus on a few case studies where capillarity is relevant. So first topic is really about the granular materials. First of all, I think maybe we start with the packing of cohesionless, where there's no interparticle forces. So normally it's quantified by the packing fraction, which is the volume of the solid over the volume of the total space. Okay, so that's the dimensions number ranging from 0 to 1. And other people may use the porosity, which is the 1 minus the packing fraction to quantify the packing structure. And existingly, we know that there are several regular or ordered structure, phase center cubic and body center cubic. They have pretty good analytical solution and understanding. And then there's a random packing ranging from random close packing, random loose packing, and random very loose packing with a packing fraction going from 0.55 to 0.64. And depending on the packing method and also the type of materials, mainly the friction of those particles, then they can range from a lower bound or upper bound within approximately majority, it's pretty close to 0.6. That's for cohesionless packing of monodispersed spheres or the spheres of the same size. And then if we decrease the size of the particle, so here it's a pretty old study looking at the porosity as a function of diameter of glass beads. So it's in centimeters. So basically here we are looking at is 0.1 millimeter or 100 microns, 200 microns, 300 microns. We can see that in the vertical axis, we got the porosity. So when the particle is large, then the porosity is pretty close to 0.4, which is consistent with a cohesionless particle with a packing fraction of 0.6. So 1 minus 0.6 is 0.4 of porosity. But the particle size becomes smaller and smaller. We can see that the porosity becomes more and more, becomes larger. And the reason for that is due to the van der Waals force becomes more and more significant as the particle becomes smaller. So there's expressions to evaluate what is the interparticle force. At the same time, if we have look at the capillary force, then this graph shows the porosity of glass beads as a function of liquid content. So adding a bit of water. So when adding small amount of water, we can see that the porosity increases, reaching kind of a plateau regime, and then as you add more and more water, it eventually decreases. The reason of this increase in porosity is because of the cohesion from the liquid bridges. And then there's an interesting plateau regime. This is because that um, the size of the liquid bridge doesn't significantly influence the force, because overall the interparticle force is equal to a pressure multiplied by the area. So the area is indicated by the red color. As your liquid bridge becomes smaller or larger, there's a balance between increased pressure and decreased area. So in the end, the multiplication of those two give approximately the same force, leading to this apparent plateau regime in the overall granular um, porosity. Okay, overall, it's pretty interesting, and the existing model that has been used to describe the packing fraction is by proposing a force ratio. So we know that the particles fall down because of gravity. We know that the interparticle force play a role in this. So intuitively, we can establish um, a ratio between the interparticle force to the force of gravity, and then plug this R into this equation. We can see that overall the line can well describe all the experimental and numerical data. So that's from the existing literature. But one thing we kind of realize that is missing is maybe the overall packing fraction is also depending on the process, namely how to actually generate this packing. In some literature, they just mentioned that in simulation, they let the particles fall down. And then in some experiments, they just used a funnel to pour the particles into the beaker or the container. So basically, how do you pack those particles should have an effect on the resulting packing fraction. So um, to investigate this procedure, we kind of set up an experimental like packing procedure. And here's a schematic. So we have a vibration machine with a container, and within which we have some kind of wet granular glass beads. And then basically the vibration machine start moving, and then all the particles falls down. And then falls down into a container that is sitting on a strut that is disconnected with the vibration machine. So basically, the main parameter we are controlling is the size of the glass beads as well as the height where the particle is falling into the container. All right, so quickly the results. On the y-axis, we got a packing fraction, which is the dimensions number going from 0 to 1. And then the horizontal axis, that's the size of the particles. For all the colored dots, that represents the different free fall height, going from 80 millimeters to 300 millimeters. First of all, we can see that as the particle become smaller, the overall packing fraction is smaller. At the same time, we see that different colors, like if the color goes from red to yellow, so going downwards, we see that the packing fraction also decreases, indicating that if you have a smaller freefall distance, then the packing fraction will be lower. The overall packing structure is more sparse. So then we can formulate impact from an energy perspective. We can form a dimensionless length based on the impact energy and energy dissipation. So impact energy we can estimate as the kinetic energy upon impact, which is directly converted from the gravitational potential energy incorporating this H4. And then for the energy dissipation, we have the interparticle force. And depending on what system we are considering, if we consider dry powders with van der Waals force dominating the system, then we will just calculate the force using the bottom equation. Or if it's a wet granular material, we use this FC equation to calculate the F interparticle force. And then we can see that using the same relation, we have the packing fraction as a function of this newly proposed dimensionless length, and all the data points falls onto a single line. This line also not only describe all the experimental data where we did with the wet granular material, but it's also applicable to particles that are dry powders with van der Waals. Okay, so overall good, we have a like better understanding of the packing structure. But right after this work, we are looking at this figure and thinking about the original cohesionless packing structure. Well, we know that this red dashed line, which is 0.55, if you remember 2 slides before, that's the lower limit of random, very loose packing structure for monodispersed spheres. That actually means that if we dry the material, then all the points, the purple, yellow, and red, should collapse upwards because theoretically they cannot be stable under such low packing fraction without any cohesion. So we anticipate that collapse upon drying, then that's what we did. So I have a video over here showing the drying process of wet granular material. So I'll just play this video. Maybe I just over here, I just want to show you that during the initial drying process, we can actually visually see there's a drying front propagating downwards. Okay, and then towards the end of the drying process, we did see some collapse of the granular material. And then we went on to other experiments like using the nuclear magnetic resonance to evaluate the spatial and temporal distribution of the liquid, as well as plotting the drying rate as a function of time. So initially it's a diffusion limited regime, and then after around 15 hours, marking the propagation drying front almost approaching the very bottom, then we kind of see a enhancement in drying rate. Because if we plot the drying rate to the power of -2, we anticipate a straight line, a linear line in this graph for the diffusion limited drying. But here, clearly, there's a deviation from this diffusion limited drying, which we attribute to Kelvin effect. But I think overall, I want to dive into too much detail. And if you're interested, you can have a look at our paper. All right, so that's the end of the first part about the wet granular materials. And then the second case study is droplet movement. First of all, I think I just want to bring a few papers that inspired this study. So in the past, people have studied the plans of how liquids spontaneously move in the surfaces. So for example, here is a Nepenthes atala, where if you put a liquid in the inner side of the peristom, then it will spontaneously move towards the outside. But if you put a droplet over here, outside, then it will not move inside. So this is kind of a unidirectional movement of liquid or spreading of liquid. And then in the cactus, we have the conical structures, and then the liquid normally moves from the tip of the cone shape towards the bottom. It can also move in the anti-gravitational direction. Over here, you see that it's moving upwards. Additionally, the spider silk, where the liquid tends to move from the joint towards the knot. Okay, there's another example of spontaneous droplet movement and coalescence with a roughness gradient. So overall, there's a different categories. The first big category, I think, is the wettability gradient. That's because either chemical treatment where you treat the surface, so some region becomes hydrophobic and it gradually becomes more and more hydrophilic, which is in this study, so that the droplet spontaneously move or tends to spread towards the area that is more hydrophilic. And then even if you have the same intrinsic or chemical property, you can also play around with the roughness of the surface, such that by increasing or decreasing the roughness because of the Winslow or Casey wetting state, you can play around with the apparent contact angle, leading to basically effective the same thing. So in different regions, the apparent contact angle is different, so that the liquid spontaneously spread towards more liquid philic region. There's also structural gradients. So you see that there's a triangular shape or wedge shape, then the liquid can move spontaneously from the tip towards the region where you have a larger hydrophilic region. And then lastly, you have the conical structure where the liquid moves from the tip of the cone to the bottom. All right, so let's focus on one aspect, which is the planar surface, which is a common place with the common scenario in microfluidic devices. To achieve the directional liquid spreading, what people normally do is that they coat surface with two different materials. So here you can see that you have copper or aluminum. And then because of the aluminum is more wetting to the liquid, so if you drop a liquid over here, it will spread preferentially within the aluminum area. And then here, similarly, you can coat the surface with a certain shape, and then the gray area is hydrophilic, where the surrounding is hydrophobic, such that when you put a liquid over there, it will preferentially follow the hydrophilic regime. So surface treatment or coating must be applied to ensure the controlled droplet movement on a planar surface. But what about a surface that we don't apply different materials? This is kind of a complicated coating process. So the idea is really coming from the sharp edge pinning effect. So I talked about this study where there's a directional liquid spreading. The reason, if we zoom in, is a schematic over here. The liquid will move towards the right, but on the left edge, we see that there's a very sharp edge over here, preventing the liquid moving towards the left direction. And this phenomenon is really not too complex. Like here, here's a kind of an experiment where you can just do it on your own. You have a coin, and then you start dropping the liquid onto your coin. So by this stage, we see that the solid is kind of a wetting to the liquid with a contact angle approximately maybe 50 or 60. And then as we drop more and more liquid, then you see that the droplet expands, but the contact angle remains 50 or 60 because that's what expected. It's a homogeneous wetting surface. But as the liquid reaches the corner of the cone, you can see that it kind of start to appear more and more hydrophobic. So I'll just follow. You see that here it's kind of on the interface is pinned over here, which is exactly the same mechanism that leads to this pinning. But of course, if you continue like adding more and more, eventually up to a upper limit, which can also be calculated, this liquid will be spread laterally. Okay. Okay. So based on this idea, it really inspired us to design a surface that looks like this. So basically, we have a planar surface, but instead of doing lots of coating with different materials, we can cut two grooves into this surface such that there's a sharp edge along this line. And then when we drop a liquid, we anticipate that the droplet will not spread laterally, but it will move towards the positive X direction. And we manufacture this surface, and then which is good that we see the spontaneously the droplet moves. And then we can analyze this problem by looking at the force balance. So this is a top view of the droplet. And then this solid black line is the shape of the groove. Okay. And then we can recognize that the driving force is really the surface tension force along these orange lines. And then that's the actuation force, FC. Then we have a multiple potential of resisting force. First of all, we have the viscous dissipation from the droplet. We also have the contact angle hysteresis from the front and a tail edge of the droplet. Because the droplet is moving towards the right, the contact angle along this side and this side can be different. So that's the contact angle hysteresis effect. And then potentially there's a gravity. If we have a certain inclination angle, the droplet is climbing up, then that's another resistance. All these forces can be calculated based on the analysis of the droplet without any fitting parameters So that's the model. And then here's a schematic of the advancing and receding contact angle when the droplet moves. So advanced side, receding side. Here's just a tilt angle. But in our experiment, we didn't have any tilting angle. We just consider a flat surface. So we did further experiments with different initial location of the droplet as well as different droplet size. And then we compare this experimental measurement with the proposed model. So overall, it have a good agreement. So here it's x as a function of time. So put droplet location as a function of time, as well as the final location of droplet for different volumes or different shape of the groove. So we cut straight lines and also the curved line, convex shape. So we validate the model, then we can really use the model to investigate what is the effect of the shape, that whether it's enhancing or suppressing the movement of the droplet. So that's just a few results. And then we notice that a convex shape, so basically it's opening with a opening angle becoming wider and wider, it's better for achieving longer droplet movement. So here, that's just a comparison of the droplet movement distance. So the black dashed line is the convex shape, and all the blue lines is the straight opening angle with different opening angles, alpha. We see that overall the convex shape is better than any of the straight edge cases. We can also analyze this from an energy perspective. So how much total input energy we have, what is the total energy dissipation in order to optimize the shape of the wedge such that we can enhance the movement of droplet. So overall, greater total energy input can be achieved in a convex shape. And then there's also more efficient energy consumption, so that our conclusion is convex shape should be preferred compared to straight edge. So that's the second part, droplet movement. And then third part is about flow control in porous microfluidics. So first of all, again, I just want to present a paper that inspired our study. So what they have achieved in this study is they use 3D printing, and then by controlling the density contrast, for example, here the porosity is lower than the region outside the region, so that when you inject a certain hydrophilic water dyed in green, then the liquid preferentially fill all those paths. Okay, and then by using this one, you can achieve different functionalities. But we identified some research gaps. For example, what if the material is not hydrophilic? Because in this study, they have the material and then they also apply special coating to the entire structure to make it hydrophilic, such that when injecting liquid, it spontaneously moves towards a certain region. Second question is how to take limited manufacture resolution into consideration. In this paper, they use pretty advanced high resolution 3D printer, but depending on which machine you're using, there's kind of intrinsic manufacture resolution. Let's say 20 micron, 50 micron. When you're trying to print 100 diameter cylinders, you actually printing plus or minus 10 micron. How do we take this into consideration? And lastly, in this study, they achieved the fluid pathway by geometry. By geometry, I'm saying just the contrast between the density of the or packing, not packing from the porosity of the solids. But what about control fluid path by fluid property or flow condition? In order to understand this problem, it's very important to understand the fundamental mechanisms of fluid motion in porous media. And multi-phase flow in porous media indeed is quite an old subject, so it's relevant to carbon dioxide geosequestration, enhanced oil recovery, and other engineering applications. And fundamentally, there are very rich physical mechanisms at the micro scale. So I just quickly run over this. depending on the ratio of those two fluids or the capillary number, which is the ratio of viscous to the surface tension, you may have very different invasion morphologies, as well as the influence of contact angles, snap-off events, film flow, where if you have a wetting solid, then the liquid tends to preferentially wet the corners of the flow. Sharp edge pinning effect, that's basically the same as the mechanism we have been exploiting to achieve spontaneous droplet movement I talked earlier. And then the Casey-Winslow transition and Heinz jumps. I won't go to detail, but it's just want to show this quite interesting problem that people have been focusing in the geotechnical or petroleum field. And then for me in the past, I've been studying this problem using lattice Boltzmann method in the next slide. So I did lots of like simulation of fluid displacement in porous media, looking at how the disorder or heterogeneity affect the flow. The lattice Boltzmann method can also be used to simulate the diffusion and consumption of oxygen, the gas diffusion layers in fuel cells, as well as electrohydrodynamics controlling the fingering shape by electrical field, heat transfer over here, or contaminate dispersion. So that's a quite powerful methodology. But also at the same time, I realized I really want to further accelerate the simulation because still it took several days to run one simulation. So a focus of my past study was to develop a pore resolved interface tracking algorithm. So basically in the um, porous media flow, we know that normally the Reynolds number is not high. There's no turbulence. So instead of solving the Navier-Stokes equation, we can just look at what is really happening at the pore scale, how the interface moves. I think I won't go into too much details, but there's a different events representing how the interface touching the next particle splitting into two interfaces, or there's a multiple interface merging together. So by developing this algorithm, we can simulate, for example, arbitrary geometries with non-uniform wettability. Here's just demonstration. So we have a tube where liquid is injected from the left, and then we have four different cases with different wettability: hydrophilic, hydrophobic, half-half, and then transition from hydrophilic to hydrophobic. We can see that the interface shape moving within the tube, and then there's a switch from hydrophilic to hydrophobic. And then we can compare this method with the lattice Boltzmann method by simulating injection of yellow fluids within a porous material. So here we have a point inlet and point outlet on the left top. So overall, you see the growth of the yellow fluid and also the overall invasion pattern is quite consistent with this lattice Boltzmann method that eventually solves the Navier-Stokes equation and the pore resolved interface tracking algorithm. But the bottom one only takes less than 1 minute to run. Okay, so this algorithm is available online. So this algorithm enable us to study lots of stuff by looking at the contact angle effects in natural sandstones, study the particle effects, or because it's so fast, we can generate huge amount of data, and then to explore the capability of data-driven machine learning method for pore scale modeling of in porous media. So just going back, how does the knowledge of flow in irregular or disordered porous media help us to achieve the flow control in artificial porous structure? So we ran some simulations focusing on the regular case. This is a radio injection experiment where the blue liquid is injected from the center. And then we see that depending on the packing fraction, only difference really between the top and bottom is the size of the particles placed on the triangular lattice. We see that on the top, we have a hexagonal growth of the liquid, whereas at the bottom, it's more random. Experimentally, it has been observed on such systems, most people have look at this hexagonal growth instead of this irregular shape. And then we really searched a lot in the literature. And one study, they actually pointed out, saying that in this kind of a regular artificial porous media, most people have focused on the porous media with relatively high porosity, whereas a lower porosity has been majority like unexplored. So we know that contact angle plays a role. We know the porosity plays a role. So we run lots of simulations. In the next slide. So here, that's in the vertical axis, that's the packing porosity. And on the horizontal axis, that's the contact angle. We see that there's a transition from compact and hexagonal shape to irregular or capillary fingering regime. And then we derive, looking at, again, going back to the pore scale interface instabilities, we can kind of analytically derive what is the phase diagram. Again, the details is in the paper. But if we map the transition of this overlap to the other two, so if we map this line in the porosity contact angle to the simulation result, we see that overall it gives a good prediction on where the transition happens between the hexagonal growth and the irregular shapes. We also apply the same analysis onto different structures. So here, all the particles are placed on a triangular lattice. But what happens if we have a square lattice? Again, we have the analytical line, and then we run the simulation. Clearly, you see that instead of hexagonal shape, we have the rectangular compact shape in this overlap regime. And then on the right-hand side, we have the burst regime. Okay, so understanding this phase diagram will be useful in terms of designing the porous media. We know that in the burst regime, the flow preferentially fills high porosity regime. In the touch regime over here, so it's a pretty low porosity. The flow will preferentially fills low porosity regime. And in overlap regime, flow will expand compactly, either hexagonal or rectangular, depending on the lattice structure. So we can use this information to design our structure, no matter what the wettability is, whether it's hydrophilic or hydrophobic. Here is the simulation in comparison with experiments. We can kind of use the geometry to control the fluid pathways for both hydrophilic and hydrophobic cases. And then on top of that, from this diagram, I don't know I have time, but we can kind of create a hierarchies of different size of the particles, such that not sure you can see the green color, but the red is the smallest particles, green is the intermediate one, and then blue is the largest particles. By designing this different size of particles, we can kind of achieve the sequential control of fluid invasion. So on the left, we have the liquid move upwards, move left, filling the branch, and then move over towards the right, fill another branch, and eventually move downwards. In the other case, we have the liquid filling the entire stem or main flow pathway, and in the end, they fill those two branches. So overall, you have the same pattern, but the order of filling can be well controlled as well. On top of that, we can design a porous media such that depending on how you run the pace, for example, you put the microfluidic flat on the wall, meaning the gravity is into the page, then the liquid will go up and right. Or if you lift this small chip up, even though it's like centimeters high, very small, but again, we have control on the fluid going to exit from the other outlet. Then wettability control. So basically we have the same chip, same structure, but when you're injecting different fluid into the porous media, depending on hydrophilic or hydrophobic, it may spontaneously go towards the right, or it may exit domain from the left. Because you see that we are kind of, again, exploiting the fact that depending on where the flow condition is sitting within the phase diagram, we're utilizing the pore scale mechanisms to guide the flow. We also did some experiment without purely focusing on water. So we use some conductive paint, which is much more viscous than water. And then again, we are able to achieve this controlled pattern within this porous open microfluidics. But in this particular experiment, we really need to slow down the injection speed because from the analysis, again, the key is to make sure the capillary forces is much larger than the viscous pressure drop. Because we have much more viscous fluids, then we need to reduce the injection speed. Okay, so this experiment, I think, although the scale is pretty small, but it took 1 hour approximately to complete. All right, so that's 3 case studies and then some quick summaries. First of all, we proposed an energy-based universal model to describe the packing fraction of cohesive particles. And the model works pretty well from millimeter-sized of particles to nano-sized particles. By exploiting the sharp edge pinning mechanism, we designed the surface to enable spontaneous droplet movement, and then we optimize the overall shape for enhanced movement distance. Lastly, we kind of want to emphasize the knowledge from multiphase flow in disordered porous media can be transferred to engineered microfluidics. An example is the study where we achieved the precise temporal and spatial control of fluid flow. And lastly, I just want to summarize in terms of the dimensions numbers. So first important number is the bond number, so gravity over capillarity. This is very important because in the spontaneous droplet movement example, we need to ensure the droplet is not large because otherwise it won't remain a spherical shape, which is the key assumption in the development of the model. And the bond number is relevant to other processes like water infiltration into soils, seesaw and pendant droplet shapes, or capillary rise. The other dimension number is the Weber number, which is the ratio of inertia to capillarity. And then in the study of wet granular packing, if we really go back to and look at the proposed dimensionless length, it's actually a modified Weber number, where on the bottom we have the contact angle over here in the denominator. And this Weber number is also important in other processes like droplet impacts on surfaces, droplet breakup in spray nozzles, and droplets collision and coalescence. Last axis, that's the capillary number, so it's a ratio of viscosity to the surface tension. In the very bottom case where we do the multi-phase flow microfluidic experiments, one important thing really is to ensure the capillary force dominate over the viscous pressure, so that we need to kind of ensure the injection rate is slow enough. Otherwise, if we inject very fast, it will kind of expand more uniform, more compactly, dominated by viscous forces. So that's a key parameter in the third case study. And this number is important in fluid displacement in porous media, contact line dynamics, like looking at the dissipation of viscosity near the triple contact line, and also droplet generations in microfluidic devices. And then in this axis, really towards the origin in the middle part, that's where the physical process will be dominated by capillarity or interfacial tension. With that, I'd like to acknowledge all the collaborators and mentors that was involved in the studies, mainly from Queensland University of Technology, the University of Sydney, the Navier Laboratory at Equality Bond Paris Tech, Yuming University, and I would like to acknowledge the financial support from ARC. And lastly, last slide is I just want to briefly mention a journal which is called Capillarity. It's a kind of a new journal. And if you have some capillarity surface tension driven phenomenon, you can consider this journal. And with that, I'm happy to handle questions. Thank you very much.
Thank you so much for delivering actually this informative presentation. I really enjoyed that. So if we have any question from our audience, either just speak up or type your question in the chat box, please. So meantime, maybe I can ask my question. What actually you try just to cover the different application of this research, and what are other potential application actually you think about this research? And you briefly mentioned about the machine learning. So this research, how can actually benefit from the machine learning or generally AI tools?
Yeah, thanks for your question. So first of all, I think applications of this phenomenon, I kind of briefly mentioned them.
Yeah.
So for example, in the spontaneous droplet movement case, there's application of harvesting water from the atmosphere or spontaneously separating water and oil mixtures. Probably that's relevant to water purification or filtration. And then the other applications like carbon sequestration or enhanced oil recovery or other like fuel cells where you have hydrogen, oxygen generating water within a porous materials. That's also relevant. But specifically for machine learning, I think the key potential capability is handling the heterogeneity in porous media. Because in lots of applications in the geological context, people try to predict what fluid flow within the unknown geological space. They may have different minerals, they may have different pore size distributions. With underground, there may be fractures. So there's a huge amount of uncertainty that is unknown. So by using machine learning, I think with data-driven combined with the continuum modeling from the physics, I think it has the potential of achieving better accuracy considering the uncertainty involved in the geological formations. Yeah.
Thank you so much. Appreciate it. Any other question?
Maybe I ask some small question. First of all, thank you, Zhongzheng, for the very nice presentation.
Thank you.
I really enjoyed that too. And just a note, for some reason, your video has become blurry, like now towards the end. So I don't know if it's the
Okay,
light
yeah.
or your camera, but if you can fix it. I just wanted to ask about the experiments you did in the third part. Yes, now the video is great. What's the physical dimensions of the models? Like, what is the order? Are we dealing with micrometers? So both the pores and the overall model dimensions.
Yes, I kind of briefly mentioned over here. So is this what you're referring to? So
Oh,
that's
yes, I think I missed
12
that.
by 2 millimeters. So I think overall size of this device is similar to the size of our nail. So it's just like a 1.5 centimeters.
Okay.
And then the depth is around like 250 micrometers. Here is 300 micrometers. That's the height into the page.
Yeah.
And this particular image shows the PDMS. So it's we use the 3D printing firstly to print out the mold, and then we cast the PDMS onto the surface to make the pillars because the PDMS is transparent. So, and also we can change the wettability or contact angle of the PDMS. So that's why we chose those material.
Perfect. Thank you. Very interesting.
Thank you for your question.
Any other question from our audience? Okay, thank you so much. Once again, thank you so much for actually accepting and delivering this actually beautiful talk. Appreciate it.
Thank you very much.
Thanks.
See you.
See you. See you, Scott. See you.